Welcome to the Snowbank Mountain area. It's called Snowbank. Snowbank Peak is behind the FAA towers over there. It's because as you drive up from Long Valley, from McCall, you see that mountain the whole way. And there's often a snowbank that will persist on it through about August, late July, August. So you look up when you're at 80 degrees, 90 degrees down that valley, and you see it. Okay, so that's where we are. We're going to make a couple stops up here. Before I forget, we have a gold pen that was lost at the last outcrop. Make sure.
Hey, Joseph.
We have a winner. Next, logistics. We're here because there's a bathroom. It's unfortunately a single shooter, so feel free to use it whenever you need to use it. Drive down to your car if you need to use it, whatever. We're going to do this stop more like a geology stop than we've done other stops. So usually I park high because conservation of elevation is one of our rules. But that's all right. We'll just do a little stroll through here. We're going to walk up this ridge. We're going to spend about an hour looking at these Migmatite rocks. We're going to talk a little bit about Garnet. We're going to come back to the car, and then this is what geologists do. We're going to go sit on this ridge in a big group. The one right behind us has a nice view over the valley, and we're just going to have lunch. We're doing that so it's close to the bathrooms so that people can wander off to use the bathrooms. All right, so that's the stop.
Perfect.
All right, back to the map that Ellen showed last time. We are past the Payette River tonalite here. We are now into the Migmatite domain. So the Migmatite domain, the units here are different from the units we saw before. The Western Idaho Shear Zone deforms different things, what's there, except for the Payette River tonalite, which is always there. There's a couple interesting things that really mattered about this area. One is this screen, which is we're not going to see. This is by a place called Sage Hen Reservoir. It's a screen of old rocks, which was really useful for telling you conditions. It turns out the conditions here were about 4.5 kilobars, and they deformed. So what is that? That's about, say, 14, 15 kilometers down in the crust. So 10 miles deep, because they've got the right minerals. They've got garnet, they've got biotite. How the temperature was about 650 degrees, so it was really hot, but we know that because the granites are intruding it. And they're quartzites, so they were old sandstones to get metamorphosed to quartzites, but if they're sandstones, they have detrital zircons. The zircons say that this is North America, unambiguously North America. This is Windermere Group, looks just like it. Okay, so these have 1.1 billion year old, which is mid-continent rift. There's a bunch of 1.1 billion year old zircon. The other thing that's really interesting is this domain of Migmatite, as Ellen pointed out, happens as you go from a north-south to a north-northeast trending. I don't quite understand it. That's all right. One day somebody will figure it out for me and I'll be very happy of why that's here, but we'll get to it. So that's really what we're looking at here. So moving then, or this map then is this map. So Nicole noticed it, and then I called a geology colleague of mine, and this is how it works, who works on Migmatites. I was like, you want to come work on some Migmatites? And he did. And this was Seth Krukenberg, and he worked with a graduate student named Will Montz. And they mapped out in detail what goes on here. So we're here at Potter's Pond in this area. We're at Potter's Point, so that's Potter's Pond.
That'll get you ready for next week.
Yeah, exactly. I've never had an undergraduate do that to me. Probably good.
They're getting bolder, aren't they?
So when Seth's worked on a lot, he said these are the most complicated Migmatites he's ever looked at. And I'll explain why. Which is there's two Garnet ages. They're right next to each other. One's on just one side of Potter's Pond. The other is just on the other. We're going to walk from one side to the other. they have different ages, and that's crazy, right? Why would they have different ages?
How
if
much
they're right next
how
to
much
each other?
difference is there distance?
Distance is a couple hundred meters. This is a 110 million year old Garnet age, and this is 90. I think this is the 99, and then there's one Garnet age down here that's 97. So the 99 and 97 are Western Idaho Shear Zone ages. The question is, what's the 110? Right? So more of that about that in a second. Migmatites. These are rocks where, how do I want to say this? You have to have a strong sense of imagination to work in a migmatite. There is order, but you'll look at them and you're like, this rock, this like got beat with an egg beater, right? And the reason is there's melt everywhere, everything's flowing everywhere. We have boudins, although if you want to order the sausage, I've been told it's really boudin. Did you get that? All right, so I just don't want anybody to order a rock when you go to New Orleans. So these rocks then they melted twice. They melted during the Salmon River Belt, where all that deformation we saw yesterday at Riggins, right? The Riggins rocks had to be at least here. The minimum offset on the Western Idaho Shear Zone would put them here. More likely, they were further south, closer down to Boise. Okay? So those rocks are way away from here. But, you know, they might have been here. Anyway, and so these rocks melt. So the same deformation we see at Riggins, that early Cretaceous stuff, the migmatites, and it's particularly these and this little finger, and that finger is what contains the 110, are actually the Salmon River Belt. They are being deformed and migmatized in the Salmon River Belt. Then there's a second migmatite deformation that works on top of that that's Western Idaho Shear Zone related. So it migmatites, then shears, then migmatites, then shears. So that's complicated, right?
Yeah.
So that's
Basil,
what
but
it
they're
is.
hanging out at depth the whole time.
They are hanging out at depth the whole time. They have to be, right? So when you look at these things, then you're going to see there's like diatexics, metatexites. There's basically dark colored rocks. We have a fancy name called melanosomes for that, but they're dark rocks. And we have light colored rocks, which are leucosomes. And basically the leucosomes are melt. They are places where the rock melted. And the melt is moving out, and melt does weird squiggly things. That's why it's so squiggly. All right? And so that is a lot of this domain, but that's all through this domain, as you'll see it shot through. So on this diagram, for instance, you're going to see the dark rocks, these melanosomes, which are rocks that are getting squeezed, and then they're coming out in little squirts, coming out and cross-cutting them. They are melting in situ. And to take a rock, to melt this kind of rock, you need to get up to about 700 degrees minimum. Okay, so these are hot rocks.
That's Celsius?
Yes, Celsius. And so this is trying to explain sort of this is a simplified cartoon. And if that's simplified, that tells you what you're dealing with, okay? So, and if you look at just a result of melt, I don't think you need to move too much, Nick, you would see something like this with these dark things, which are garnets. All right, so I see garnets, I'm like, eh. But there are other people who really love garnets. And Stacey's going to tell us a little bit about what you can do with garnets. Because I should love garnets more than I do.
Hello. Hopefully there's other garnet lovers in the crowd.
Yeah.
Okay. So garnet, the reason why we care about it is I'm a metamorphic petrologist, so I look at those rocks once they've gotten cooked, and I'm trying to figure out how they got cooked and how they got back up to the surface. And so to do that, we have to calculate pressures and temperatures, and garnet is a really awesome mineral for doing both of those things. So we can look at how elements are exchanging between garnet and other minerals like the biotite that's in the rock, which is all the black stuff that you're seeing within there. And it turns out how iron and magnesium partitions into those two minerals is temperature sensitive. So we can go in and measure the chemical composition of those minerals and then figure out temperatures and do a similar thing to figure out pressures. So that tells us how deep those rocks were. And then we can look at the tectonic history and the structural record from people like Basil and Ellen to then try to figure out how they got buried. And then the other thing that garnet's great for is we can date it, right? So then we can figure out when those rocks were also deep and tie it into the tectonic processes as well. And so to date it, we look at parent-daughter isotopes and looking at that half-life kind of decay history. And so with garnet, there's two different systems. We can look at lutetium, hafnium, or samarium, neodymium, and use both of those to calculate ages. And so that's what people have done here to figure out that 11 million year or 10 million year difference between there. So just a quick garnet summary. Any questions on garnet?
So how 11 million? If the garnet's there, how? What temperature did you say, and what age?
I don't know
We
exact.
didn't do the temperature on it.
Okay, there isn't actually. Yeah, they call that thermobarometry.
So
But probably we know garnet. Garnet won't form until you're at least 500 degrees. And then generally to get the in situ melting, you're getting up to temperatures of at least 650, 750 degrees. And what happens at that point are the micas, which have a lot of water in their mineral structure. That water becomes unstable and they break down. And essentially, water is always a catalyst for reactions. And so what it does is it lowers the melting temperature, and so those rocks can start to melt. And so migmatites we think of as evidence of partial melting, right? And that's where we still have the darker layers, where we still have parts of the rock that didn't melt, and then we have the white layers, which are that part of the rock that did melt.
So do you run the dating service or do you send the stuff out?
Depends on the person. There's not that many labs that can do these processes because it does involve buying a mass spectrometer and also having a clean lab because we want to make sure to not contaminate it with isotopes from the surrounding kind of lab environment. And then the other part is you're dealing with pretty nasty chemicals like hydrofluoric acid because you have to dissolve the garnets to then measure their isotopic composition. Hydrofluoric acid is pretty terrible to work with, so you work in a pretty controlled environment for that. So you can either collaborate with labs who do this work, and sometimes we'll send graduate students to go work in that lab and get trained, or we might actually work with that lab and work with one of their existing students to have them do the work.
I'm sure they've got to be certified then, the labs.
Yep, exactly. They work with their local environmental health and safety office on campus to make sure that they have all the safety protocols and all that good stuff.
What's the error band or uncertainty with those dating processes?
It's about 1.
Plus or minus 1 million year. And what they do is they typically measure the amount of those elements or those isotopes in both the garnet as well as the whole rock, and then put those together on a diagram and then connect kind of the dots. And the more analyses you do, kind of the better your line is connecting those points and the lower the uncertainty. But it depends on kind of how many analyses you can do and also just how radiogenic it is, meaning how much of that isotope is in there to measure. And garnet can be pretty variable in terms of how much samarium, neodymium, lutetium, hafnium is there, and so that also controls your uncertainty. But in general, garnet dates tend to have higher uncertainties or errors compared to like uranium, lead, zircon data. But sometimes with rocks like this, when they partially melt, the zircon doesn't always grow during that melting. Or if it does grow, it can just be kind of a really thin layer on the pre-existing zircon. So it makes it harder to date the zircon, and the garnet's a more reliable kind of measurement of the metamorphism.
So do the zircons have those different, maybe you just explained it, but I didn't quite get it. Do the zircons have different layers in them too, like, not the zircons, the garnets have different layers in them like the zircons do?
They can. Sometimes they will, and you can get multiple garnet growth events and have garnet growing on top of earlier garnet if there's been multiple metamorphic events. The other thing that happens is you do usually get chemical zoning in the garnet, but when you're at these really high temperatures, it allows those elements to diffuse out, and so you'll lose the zoning profile, and it'll only retain the record from the high temperature metamorphic event. So it'll retain kind of the last gasp of the metamorphism typically.
So what kind of garnets do we have here? Do we have the kind that just have like a one growth?
We do, yeah. They're, as far as I know, they're unzoned garnets. Yeah. And then I haven't looked at these ones at all, but yesterday some of us were looking at garnets where sometimes you'll see they have a halo, kind of a, we call it a corona of a white around it. And garnet, as you're coming up towards the surface, as these rocks are being exhumed, that garnet will become unstable because it's happy at much higher pressures and temperatures. And so often as these rocks are exhumed, that garnet will start to break down, and it breaks down into plagioclase. And so sometimes you'll see these rims of